Cool. Thanks, Gary. All right, I'll rip into this. This is a little bit of a different talk than what you've heard so far. There's no immunology in it, so I apologize. How do you get this to go forward and backwards? Wait. Okay, cool. So just briefly, for the talk, I'll talk about the team and the capabilities and expertise, give a bit of background for the Fast Start project that we're running, and the objectives of the project and the progress to date. This is my acknowledgement slides, just to say thank you to my team up front, because I know I'll run out of time at the end. So yeah, James, Renu, Dan and Kevin have done a huge amount of work that have really enabled this Fast Start project and given us the expertise we need to do the stuff that we have promised and are able to offer to the platform. So this is what the team does. There's a lot of chicken wire on this slide, but we're interested in nucleosides and nucleotides, which basically are the building blocks, specifically around the antiviral activity over the last 5 years in particular. But we're also interested in narrow spectrum antibiotics based on mechanism-based inactivators, and we have some projects on bile acid therapeutics. So 5 years ago, MB had the foresight, 2 months before the pandemic started, to fund a 13.7 million antiviral research program on small molecule drug discovery. And so these are the two molecules that we're interested in, DDHC and galidesivir. So small molecule antiviral nucleotides, most of you will know, are basically defective building blocks that the viral machinery incorporates into its RNA or DNA. And so we attempt to make defective building blocks which are preferentially taken by the viruses. They have a variety of mechanisms of action, and the two we're interested in are sort of slightly different mechanisms. This DDHC molecule, I'll talk more about shortly, doesn't have a 3' hydroxyl group, so it's effectively a cap and a chain terminator, an immediate chain terminator, whereas some of them do possess a 3' hydroxyl, like galidesivir, for example, which gets incorporated into the RNA chain of an RNA virus. And then you have some chain extension, is known as a non-obligate terminator, and these operate by a variety of mechanisms. Okay, so the first project on DDHC without the 3' hydroxyl, an obligate chain terminator, came out of our long-term collaborators, Steve Almore and Tyler Grove at the Albert Einstein College of Medicine, discovered where the antiviral properties of this interferon inducible protein come from. What it does is essentially dehydrate cytidine triphosphate to give DDHC cytidine triphosphate without the alcohol that can no longer extend the RNA chain. So the idea of the project in the program was to develop antivirals based on this endogenous antiviral ribonucleotide and develop a good antiviral drug based on that. To do this, we had to develop some chemistry, and the first thing we needed to develop was a way to synthesize the DDH-CTP, the molecule of interest, so that we could undergo biochemical evaluation. So we did this by a couple of routes and ended on a key intermediate. We realized this was pretty key to developing lots of prodrugs. At the time, we didn't have any antiviral activity, so we filed methods of production patent or a process patent on how to get to DDHC type analogs, and James Wood, a very talented chemist in the team, managed to make DDH-CTP on a gram scale in a single pass using this chemistry he'd developed. So at some point shortly after that, Otago University got some money from the Ministry of Health and contacted us to try and make the DNA triphosphate building blocks for homemade PCR kits, basically, because the supply chains during the pandemic started to collapse, and this was, a significant concern for not only investigation of how to cure the virus, but antiviral drugs. So to go hand in hand with this, we got almost $1 million from the COVID Innovation Accelerator Fund to look into analyzing the synthesis of small molecule drugs that were being developed to treat COVID at the time. So that was also working with Margaret Brimble's group and Bill Denny in Auckland and Glycosin to see if we needed to rapidly synthesize any antivirals to cure COVID or treat COVID, that we were in a position to do that. So we did a bench exercise and investigated lots of the work there. The other project, galidesivir, the non-obligate chain terminator, came from a long-standing 20, 30-year collaboration with Werner Schramm's group, where Gary, Pete, and Richard have developed lots of transition state analog inhibitors. So galidesivir was originally designed as a transition state analog inhibitor with picomolar affinity for its target, purinucleoside phosphorylase. But BioCryst discovered it had broad-spectrum antiviral activity. So you can't see the numbers, but it's generally pretty potent against many, many RNA viral families and not toxic to very, very high concentrations. So given the expertise we had in-house, we wanted to develop these C nucleoside analogs and make a better antiviral. So that's the two projects from the antiviral program. And one of the things we managed to do was find a way more potent molecule, which we call clinchivir. And it had very low sub-micromolar activity against influenza A and B, and so it was relevant to a pandemic context. Excellent selectivity indexes, but ultimately in an animal model, an infection model was too toxic to progress. And this was made by merging the nucleobase of remdesivir with the immunosugar component of galidesivir. One of the things we also figured out how to do while doing this research was to make prodrug forms, so phosphorus 5-phosphoramidate prodrug moieties, and that's relevant to many of the tools you can make for an RNA platform such as this. And we also made a bunch more analogs and developed the chemistry to enable a lot more synthesis around these C nucleoside analogs. So one of the other things we did was to make the triphosphate form of galidesivir, which was no mean feat, and Renu managed to do this. Renu's in the audience today. And this was used to investigate the mechanism of action of galidesivir. And indeed, we did find with Richard Kingston's group in Auckland that it didn't behave the way it was supposed to. So in the original BioCryst Nature paper in 2014, it's supposed to terminate the RNA chain extension after 3 incorporations. That's not how it works at all. But the point is we can make these really complex triphosphates, which may be relevant to the RNA platform. Given that that's not the mechanism of activity, we're interested in finding out what the mechanism is. And so we've recently made this completely novel phosphoramidite analog that we can look to incorporate into synthetic RNA to investigate the mechanism of these things. Some of the other things we've done in the team and in the broader institute are to look at these complex nucleotides, so phosphorothioate dinucleotide analogs, and also we've looked at mRNA caps in the institute in the past. So we have experience there, which brings us to the project. What is our Fast Start project? So we're experts in nucleoside and nucleotide synthesis, so we have something to offer the platform. You know, we've had experience with investigating critical reagents to New Zealand. So going back to the Innovation Accelerator Fund, one of the things that started to deplete in supply in New Zealand was an antidepressant. So could we synthesize the antidepressant, for example? So we can look to address the requirements of the platform in a pandemic setting and identify critical reagents that the platform might need to perform or continue research during a pandemic setting, and just generally supply custom reagents based on our expertise. We can support the pillars and other Fast Start projects by providing reagents and also, you know, develop new IP where possible. So to do that, we just decided to have a proof of concept synthesis for a few molecules, which I'll show on the next slide, and then establish, you know, QC methods, analytical methods, both preparative and analytical, and also talk with Glycosin, our neighbors across the way, to decide on what would be a good starting point to go into GMP synthesis for these types of materials. So just very briefly, these are the things we've identified. We'll go for the hardest things first. So N-methylpseudouridine triphosphate is one of the more expensive ones, and one of the more expensive ones means it's harder to make. So we've done that. We've made a gram of it. I'm going to skip the rest of the next few slides, but we've done that, and Renu did a fantastic job to do that on a gram scale. We also looked at the phosphoramidites, and we've also made the most difficult one, the N-methylpseudouridine phosphoramidite, which is the most expensive one that we know of. Is about $3,500 a gram, or $7,000 a gram, whereas the common building blocks, like the one, the G phosphoramidite on the bottom, is $6 a gram. So we can't compete with those prices, but if we want to rapidly access these types of things, then we can do that. The other thing, on the right-hand side, we can make fluorescent building blocks. So working with Gavin Painter's team, we've managed to make 1 gram of this fluorescent material, which is more than enough for the lifetime of probably the RNA platform to investigate things. And more recently, we've started to look into the fluorescent probes and caps, which we think is where the future of where we can contribute could be. So I'll probably stop there and say thanks, I think, to bring us back into time.